Hey, my name is Sarnath from Blockheads Academy, and in this video, I'm going to talk a bit about matrices and vectors, more of an introductory note. Many times, when we encounter matrix for the first time, we get unsettled by the notation, right? And in this video, I will introduce matrices, why they occur, what is a motivation, what is a matrix multiplication, why it is performed the way it is performed today, and what is a matrix vector transformation. So before we understand matrix vector transformation, I think we should understand what a matrix is. So let's go and figure out what it is. So what is a matrix? A matrix is just a notation or representation. At the most basic way of viewing it, it is just a notation. That is all it is. And however, notations can be powerful because they can induce a formal rigor in any subject. And in this particular case, matrix helps in inducing formal rigor while handling linear algebra. Especially, the notation originated when solving linear equations, right? We use a Gaussian elimination method for solving linear equations, and to denote this method in action, right, a notation was required, and that is how matrix came into being. In the subsequent slides, I'll give you a formal introduction to Gaussian elimination, a kind of primer, and then we will see how matrix notation helps to represent this uh, Gaussian elimination process. So let us start with Gaussian elimination, right? So let us look at this set of four equations listed here. It has four equations and four variables, like namely w, x, y, and z, right? So what we try to do here is we just write it in the form of a matrix. So as a notation, so you see 2 0 1 0 1 in the first row of this matrix. Basically, 2 stands for the coefficient of w, 0 stands for coefficient of x, which is 0, y's coefficient is 1, which is here, z's coefficient is 0, which is also recorded, and the final value that we have was 1. Everything we write it in this notation, right? So the entire system of linear equation is captured in the form of a matrix. As such, at this point of time, the matrix is just a notation. That's all it is. Now, how do we proceed further? We want to eliminate systematically so that we produce an upper triangular matrix which can be easily solved, right? To do that, we have to start eliminating 3 from the second row, right? So what we do is to achieve that, we multiply the first row with minus 3 by 2 and add it with the second row. This produces the second row in the second matrix like this. Similarly, we multiply the first row with minus 2 and add it with the third row here in the first matrix, and this produces the third row in the second matrix like this. Same case here, multiply the first row with minus 2 and add it with the fourth row. You get the fourth row in the second matrix like this, and as you can see, we have eliminated the w variable in all the three equations. It is there only in the first equation. Now we shift our attention to the second, the pivot element here, that is 1, right? We need to get a 0 beneath this and this, right? In these two areas, this is already 0, so you don't worry about it. But what to make this 0, we just have to add the second row with the fourth row, right? When you do that, you get this equation, this matrix. Now in this matrix, we look at the pivot element minus 2. We want to create a 0 beneath it, right? To do that, we multiply the third row with minus 3 by 4 and add with the fourth row. When you do that, you get a 0 here, and we have got a triangular system of equations. So basically, this means that minus 17 by 4 into z is 12, which means that you can solve for z straight away. Once you know z, you just shift your attention to the third row. You got minus 2y minus z equal to minus 2. So you already know what's the value of z, so you can solve for y. Similarly, you can solve for x here, and finally you can solve for w, and this is what is called backward substitution. So to start with, let us consider the multiplication of two matrices that you see here, right? So many people ask, right, why does matrix multiplication has to work the way it works? Now, who gave this rule? Now, what is all this? So we will answer all those questions by considering this matrix multiplication, right? So look at the first row in A matrix, right? what does it actually tell you? It basically tells that just retain the first row in the matrix B as it is in the final output, right? So which means that when A and B are multiplied, the first row will be just 2010 in the output matrix as well. So that is what it represents. Each, if you look at the row in the A matrix, each one is a weight for the corresponding row in the matrix B, right? So it's basically a weighted addition of rows in matrix B, right? Now look at this. So I would minus 3 by 2, 1 and followed by two zeros, right? So what is this minus 3 by 2 doing here, right? So what it says is take the first row in matrix B, which is 2010, multiply it by minus 3 by 2 and add it with one weight of row 2, which is 312 minus 5. So that will form the second row in your output matrix. So which means that it is again a weighted addition of rows in matrix B. But these weights have been chosen so that when you add them up, you will know that the first element in the second row will be 0, because when you say minus 3 by 2 into 2, it gives minus 3, and when you say minus 3 plus 3, you're going to get 0. So it will automatically that eliminate that number to 0, right? Just look at this. It just says take minus 2 weighted first row in matrix P and a simple third row in matrix P without any weighting, just a unit weight, and add them together. And this will form the third row in the output matrix. And again, you can see that it eliminates the first element in the first column of the resultant row, right? So this is again the same thing. I think you can make this out very easily, but by now you would have understood what we are actually doing is Gaussian elimination. When I am multiplying, when I am defining the matrix multiplication to be this kind of an operation, right? This notation of matrix has now slowly transforming into an algebra. I am defining an operation on two matrices, which will do Gaussian elimination for me. This weighted sum of rows, that is exactly what I want to do in Gaussian elimination. So by doing so, all the operations I was talking about previously, right? I was eliminating one variable, I was eliminating two variables, all that can be represented through matrix multiplication like this, right? So that is how matrix multiplication works, right? It is just a new representation and a semantics for the multiplication operation that we enforce because it solves our problem, right? The representation came to solve this problem of linear system of equations and all that, and we have chosen an operation and we have assigned semantics to it. Then that is why matrix multiplication is performed in this way. That is all it is. So you can see that after this multiplication, if you look at the first column in the output row, only the topmost row, the first row has all the variables intact. The second, third, and fourth row, we have eliminated one variable, right? By suitably choosing the weights in the A matrix. So, and by defining what matrix multiplication is, right? From this, we are able to eliminate all these things. So, it is just our own semantics for multiplication. So that is what it is. Now, if you look at it, now the problem can be repeated to a submatrix. You just take the submatrix which is highlighted in yellow and you can do the same kind of elimination operations, which means that I can start multiplying this matrix with another matrix now so that I can eliminate, and finally I can create a system of matrix multiplications which when performed will change the matrix input matrix into an upper triangular matrix, which is the triangular system of equations that I was talking about. So by representing things as a matrix and by telling what exactly matrix multiplication is all about, by defining the operator, right, we are able to take a linear system of equation and then change it to a triangular system of equations which can be solved. So that is where matrix multiplication comes into picture, and this is the exact purpose that it solves, and that is the reason why matrix multiplication is done in a certain way. It is just a weighted addition of rows, which is needed for Gaussian elimination. That is what it is. So here is a quick recap on what we have seen so far. So the matrix is a representation of linear systems of equation. That is where it originated, and by defining the matrix multiplication as an operator that we have seen so far, it helps us to denote the various stages of Gaussian elimination, where we perform the weighted sum of different rows. This is the origin of matrix multiplication. And now that we have a notation and an operator, the entire algebra was formed in later period of time, and a lot of advanced techniques like singular value decomposition, matrix factorization were all followed up, and they have a lot of applications outside Gaussian elimination as well. So with that, let us go ahead and see what is a matrix vector transformation. So before I move on to matrix vector multiplication, I would like to draw your attention to this book on linear algebra by Dr. Gilbert Strang. It has very good coverage, and it is one of the best books in linear algebra followed by many universities. So if you are interested in knowing more about linear algebra, and I would highly recommend this book. So what is matrix vector multiplication? So what do they say when they say a matrix actually transforms a vector, right? We would like to understand what it is. So before we go into matrix vector multiplication, I think we should understand a bit of what actually a vector is. Consider this vector 1, 2 that you see here. It represents a vector in 2D space, and you can see that there is a 1 dot on the x-axis, the 2 dots on the y-axis, and the vector is also drawn. So that is what that line 1, 2, the line that connects 0, 0 and 1, 2, that is the actual vector that 1, 2 stands for. An important thing that you need to know is that a vector says 1 and 2, right? But what is 1? 1 in x-axis and 2 in y-axis, right? So the axis is very important for a vector, right? A 1, 2, you will need to know on what axis that 1, 2 is defined, right? As we will see down the line, it's a very important feature. So although it's not very clear here, it's 1, 2, we just take it as a given, but the axis on which the vector is defined is equally important. So in this case, you can just think of the axis as 1, 0 on the x-axis and 0, 1 on the y-axis. These are the two unit axes, and any vector can be considered as a linear combination of these axes. So as we'll see down the line. So the 1, 2 can actually be represented as 1, 2 is a vector. You can just represent it as a linear combination of 1 and 0 and 0 and 1, as you can see on the equations here. So which can actually be represented as a matrix vector product, where this matrix is an identity matrix, as you can see from the equation. So we don't have to write this 1, 0 and 0, 1 all the time. But the point I'm trying to make here is a vector always goes along with its axis, right? The axis is an invisible guide there, which we generally ignore. But it's important to have this notion that 1, 2 is nothing but it's a linear combination of its axis. Another way to look at the vector, which is essentially the same as what I spoke before, but you can also look at it as a walk on the x and y axis. So you just walk 1 unit on the x-axis direction and then walk 2 units on the y-axis direction, or you can choose to walk from 0, 0 on the y-axis to 2 units and then 1 unit on the x-axis from there. So both of them will reach 1, 2 only. So now look at this walk. We're walking from 0, 0 to 1, 2. We're just making a lot of turns here, but essentially it is still the same. So so the idea is that you can keep walking on your axis. Let's say that a vector is defined by the axis. You can choose to walk however you want along the axis, and then reach that vector. So if you can reach that vector, the amount of magnitude that you have walked in the axis becomes what the vector is actually. So if you can look at it, on the x-axis it is actually one. It is broken into two parts, like the bottommost green and the green above that. Actually, two horizontal greens, you can see they both, when you add them together, you'll get a one. Similarly, we have just broken the two into two vertical splits, and this is also fine. It's not, it's all the same actually. Now look at this. Here we go up and then we come down. So when you come down, you're actually going on the negative of your axis. It is still fine. You are still walking along your axis in various directions, in various magnitudes, sorry. And still you reach your point 1 comma 2. So if you add the vectors, all the vectors that you see here, you basically get 1 comma 2. So that's the whole idea. You can walk in fractions as well. It's not like you should always walk 1 and then you walk 2. No, you can walk a 0.25, then you can go up, then you can turn right, you can come down, you can walk however you want along the axis to reach your vector. So ultimately, when you add up all your itinerary, you'll just get 1 comma 2. So that's the whole idea. So when we are doing this walking, what we have also learned is vector addition, because all the walks started from 0 comma 0. Then based on which direction we are going, right, we keep updating our coordinates in a line parallel to the vector representing the direction. So for example, if you want to look at the first green arrow from 0 comma 0, it can be represented as a vector addition. From 0 comma 0 is a vector and 1 comma 0 is a vector. We are just moving 0.25 in the direction of 1 comma 0, right? So essentially you go to 0.25 comma 0. That's their end result if you start from 0 comma 0. Similarly, for any x comma y coordinate that you start from, let's say x dash comma y dash, plus if you want to go in the direction of some vector like a magnitude of 0.25, you just need to say x dash y dash plus 0.25 into whatever vector direction that you want to follow. That will give you the resultant xy coordinates. So what about the random walk, right? Can I go start from a location and just randomly go on all over the places and all that? So you could, provided you have so many axes, but generally the best way to understand a vector is with respect to the axis. So you move in terms of your axis to reach the vector. So that is how you like to see it. So now that we keep talking about this axis, the question obviously is, can I change the axis? Right? Can I have a different unit axis? Should the new axis always be perpendicular? Can I just have some crisscross lines and call them as axis? That eventually leads to a question: what exactly is perpendicular and all that? So we'll talk about that a bit later in some later video. But for now, it's important to understand and ask whether can we have two different axes. So what happens? So yes, why not? We can have different axes and they need not be perpendicular as well, right? And they need not be a unit length. You can just declare an axis in which you can just take an arbitrary length of a vector in some direction and then say, hey, this is my unit axis along this direction, and take another vector, right? And then do the same thing, right? So the question is, as long as the amount of axes that you choose, they are not parallel, right, and they all intersect in a point, then every point in the space can be represented as a linear combination of the axis. When I say linear combination of the axis, you can give a new coordinate system. It can act as a coordinate system, just like how you put two perpendicular lines and then put 0 1 2 3 0 1 2 3 and say, hey, this is a coordinate system. Similarly, you can just choose two arbitrary vectors of any different length, right? Just take two vectors and then say, hey, this is my coordinate system, and we can just go ahead and start creating coordinates, assigning coordinate points to each point that in the new system. It's quite possible. So what I missed telling in the previous slide is that to represent a 2D space, you require a vector, you require an axis of two vectors, right, which are not parallel and they intersect in a point. If you have a three-dimensional space, then you need three axis vectors. Right now, let's see if I'm just drawing two new axes, right, -1 comma 2 and -1 comma 1. Can these two serve as axes instead of having two perpendicular lines? But can this serve as axes? So this is something that we want to investigate. So in this axis, what would be 1 comma 2, right? See, in the previous axis we saw 1 comma 2 nicely laid there. In this case, what is 1 comma 2, right? So 1 is nothing but the red line that you see, that is one vector, and 2 points, two units of this vector, the other vector, right? You can just put 2 units of these two vector and minus, you get minus 3 comma 4, right? This minus 3 comma 4 is nothing but uh, your new 1 comma 2 in the new coordinate system. So the 1 comma 2 in the new coordinate system is nothing but minus 3 comma 4 in the old coordinate system. So we can just write whatever we discussed now as the product that you're seeing here, which is nothing but one unit of minus 1 comma 2 and 2 units of minus 1 comma 1. If you linearly combine them, you get minus 3 comma 4. That is what we saw just now. The same can be written as a matrix vector product, just like this. Minus 1 comma 2 and minus 1 comma 1, which are the new coordinate system, which are the new axis, becomes a matrix. And 1 comma 2, which is the coordinate system, which is nothing but a coordinate for which we want to get the mapping, right? So the axis, the new axis, and 1 comma 2 in this axis, what is 1 comma 2? That is what we want to find out, and that matrix multiplication converts it and gives you the new coordinates, which are nothing but minus 3 comma 4. So the 1 comma 2 in the new coordinate system is nothing but minus 3 comma 4 in the old coordinate system, right? And this is accomplished by matrix vector multiplication. So what we saw just now is we had a new coordinate system and we want to figure out a 1 comma 2 in the new coordinate system. Where does it map to, right? So we just find out that it actually maps to minus 3 comma 4 in the old coordinate system. That's fine. But if I give a coordinate in the old system, right? Let's say if I give you minus 3 comma 4 and I give you the new axis, can we figure out what is the coordinate in the new system? What is the coordinate in the new system that corresponds to this old coordinate system, old coordinate, right? So that would essentially mean how much should I crawl or direction walk in each of these new axes so that I can reach the old coordinate point. So that is what it is. So this is exactly same as what linear equations solve. For example, just look at ax equal to b, where a and b are given and x needs to be found out, right? So what value in the new coordinate system is x, which when multiplied with this axis, which is a, will give you b, right? So x is nothing but a inverse of b. And talking about a inverses and determinants, I think it's a whole new topic by itself, so I'm not going to cover here. So this is just here for starters. So in our way of interpreting matrix vector multiplication that we saw just now, a matrix can be looked at as a set of vectors describing a new coordinate system, and a matrix vector multiplication basically figures out what is that particular vector in the new coordinate system. Where does it map to, right? So that is how we have interpreted matrix vector multiplication. That could be other interpretations as well. It totally depends on the application. And there are some special types of transformations. For example, uh, given a matrix and a vector, and when you multiply them, that is when you try to find out what is the actual coordinate in the old coordinate system for a vector. The vector does not move at all. It's just in the same place, just it gets stretched a bit, right? It does not move. In this case, we saw from 1 comma 2 we just moved to minus 3 comma 4. That was almost a left side rotation, kind of rotation as well as scaling, right? It's not simple rotation, it's rotation as well as scaling, right? So there are some cases where nothing happens except the scaling. It just expands, the vector just expands like an elastic, right? So such a vector is special for that particular coordinate system, and this such a vector is called as an eigenvector, right? But there are several applications for this. Maybe I'll cover them in a subsequent video. For now, I think we are okay to just to know that such a thing exists. So coming to applications, matrix vector products form the most fundamental mechanism of computer graphics, especially for doing a lot of transformations like shearing, scaling, rotation, translation, and others. 3D graphics too makes extensive use of matrix transformations. Apart from this, there are several other applications of matrices involving eigenvectors, SVDs, and so on. So we'll be covering them in future videos. Uh, in this video, I hope you enjoyed watching this video, and the key takeaway should be probably around the introduction of matrices, getting the notion of a matrix, why exactly it came into the picture, and obviously a sense of direction about directions, because vectors and matrix algebra, all of them ultimately are related to some direction, as you'll see in future videos. So this would be the basic takeaway from this video, and I hope you enjoyed it. So this brings us to the end of this video. If you have any feedback, comments, if you want to discuss something or include your materials in a future video and all that, you can please write to me at blockheadsacademy@gmail.com. I'll definitely read and get back to you. Okay, thank you so much.